I would like, good morning everyone.
Morning.
So today I would like to present my thesis presentation on improving the performance of parallel SPARQL query processing on Apache Spark using Bloom filters. Before going to start my presentation, I would like to thank Dr. Rao for continuously helping me out and his assurance to, and he created comfort zone for me to develop this such a sophisticated system. And I would like to thank Dr. Zeng for accepting our request and being part of the committee member. And also I would like to thank Dr. Zuli and Geeta Manjunath and Saudia Roy. And also I would like to thank Anas, Hastimal, Daniel for few other my lab members for continuously helping me out to develop this application. So these are the contents of my today's presentation, and introduction on my thesis work, and little bit of background on RDF and SPARQL technologies, and also cluster computing technologies, Apache Spark and GraphX, and the motivation that leads us to implement this such a sophisticated system, and also the parallel RDF query processing using Apache Spark. There are few existing approaches which are actually developed using Apache Spark. So I would like to give the overview of those approaches, and then I would like to go with my approach. And lastly, the performance evaluation between our approach and few of the existing approaches that are implemented for parallel processing on Apache Spark. And I have used two different cloud platforms to do the performance evaluation. One is the Microsoft Azure and another one is the Cloud Lab. So I would like to cover those two cluster configurations as well, and finally conclusion. So while coming to the introduction, we have seen nowadays resource description framework, RDF, it becoming a very popular model to represent data on the web. Nowadays we can see there are large number of knowledge bases available which are open source, and all these knowledge bases are actually employ the data in the RDF format. We are using SPARQL to retrieve the data from those RDF data sets and to do some analytics on those. So, and as we know, nowadays resources are increased more, so because of these multiple sources, we are actually, these knowledge bases are keeps on increasing. So whatever the current approaches like centralized approaches, those are not able to handle those SPARQL query processing on those knowledge bases very efficiently. So we definitely need certain parallel processing techniques where we can process such a huge knowledge bases very efficiently. So nowadays we have a lot of big data tools like MapReduce, Spark, Flink. These are actually providing huge data processing on a cluster of machines. So we can use, those are actually providing a platforms to build the scalable RDF query processing techniques. So this, because of those, so that's why if we see nowadays popularity of these, especially these tools like Apache Spark, keeps on increasing. Especially the reason behind is Spark is providing in-memory capability. So that's made us to choose the Apache Spark to implement the scalable RDF query processing in my thesis. So while going to the background on few technologies, the first one is the RDF. As name stands for Resource Description Framework. Resources are nothing but anything on the web that can uniquely identify with the URIs. These resources can be people, things, places, objects, or anything that we can uniquely identify with the URIs. And descriptions are nothing but describing features, attributes, characteristics, or relations between those with some other resources. And frameworks is actually specifies the model or syntaxes or language that how we are going to describe those things. So in combine, all this RDF stands for Resource Description Framework, which is actually specifying the standard model to represent data on the web. So this is very popular thing. The reason why is RDF represents data in the triple format. This makes RDF more popular. The reason being is multiple applications can understand the RDF data because of the triple formats, and these applications can exchange the data in this RDF format. So if we have an example statement saying that UMKC is located in Kansas City, we can represent the corresponding statement in the RDF representation as subject, predicate, and object. If we see, the UMKC is prefixed with some URI. So as I mentioned, any resources on the web that we should represent with the URI. So that's why we use the URIs to represent some predicates. It might be either string literals or numbers, or we can represent those, even those were as well with the URIs. Sorry, objects.
For SPO, are they all do they all have URIs, or just subject part has URI?
Subjects and predicates will they should definitely have the URIs, and objects can be in the either URIs or string literals or numbers. We can use those.
But for the subject part, it will always have
URI.
your URL. Right?
Yes,
Okay.
and even the predicate as well. So,
Hey, just want to let you know, I got an email from Professor Julie. He's going to join via WebEx, okay? So just want to give you a heads up, and I hope the slides you're sharing, I hope he can also see it, or every person who's joined to my WebEx link, I hope they can all see it, okay? So just want to give you a heads up. Okay, thank you.
thank you. So, I will continue with the RDF. Another interesting thing with the triple pattern is RDF graphs. If we consider any triple in the RDF data, we can derive a directed graph from that by considering subject and object as a vertices, and predicate can we take as an edge or relation between those subject and objects. So if we take the few knowledge bases, there might be the number of RDF graphs which are either directly connected or not connected. So if I just took a random 10 triples from the DataGov dataset. So I represented in the graph format for the same RDF data. So that's why here it looks like. So here it is always the directed graph directing from subject to object with predicate as a relation between the subject and object. SPARQL. SPARQL is a popular query language to retrieve data from the RDF databases or knowledge bases. So we are more familiar with the SQL query languages to retrieve data from the traditional relational databases. Similarly, SPARQL is a query language to retrieve data from the RDF data. SPARQL mainly retrieves the data with the help of basic graph patterns, matchings. So what it will do is, I will explain now. This is the syntax of the SPARQL query, how it looks like. If we see more in details, those are the return variables, which is actually bounds the variables in the RDF data when we actually query the RDF database. And if we see, these are called triple patterns, we call it as. Here in this, we have two triple patterns. The first one, we need to find out subject and object in the RDF database or knowledge base. In the second one also, we need to find the subject and object. There might be some cases where we might need to find either subject only or object only or predicate only or combination of any two, subject or object or subject or predicate or object. So these we actually called as canonical forms of the triple. If we take subject, predicate and objects, these are the combination that we can query from that particular triple.
So what do these two patterns represent? Can you explain them a little bit?
These are the triple patterns actually. So usually in the RDF database, RDF knowledge base, this might be the triple. If we see.
So what kind of query is this? Like what are you searching? Can you explain that a little bit? Just for that example, right? Like country name, state code.
Here we are actually finding out the triple which has the predicate this one.
Okay.
Here in subject there might be some other value.
Right.
In object there might be some other
Yeah,
value. We need to find out the triple which is actually having the same with predicate as this one.
Okay.
And again in the second triple pattern, we need to find out the triple which has the predicate this one. So we need to combine the results of both these.
So it's actually an AND relationship.
Yes,
Not
it's a
or,
join.
right?
Yes,
Okay.
it's a join operation.
so I understand.
Show the graph. Show the graph
Yes, yes.
representation of
Yes.
the query.
So, how exactly it works is to retrieve the data. If we give any SPARQL query, it constructs the subgraph from the given query. If you see, this is one triple. So here subject and object with this one. This is actually a predicate. I just prefixed this one with some variable and just added this one. So this is one triple pattern and this is another triple pattern. Like this, for a given SPARQL query, it constructs the subgraph. This subgraph will find the, whenever we execute the SPARQL query, this subgraph will try to find the patterns in the original data RDF graph. And if it finds any, then it will return those results. So for this query on the previous RDF graph, it returns these values. Subject value as this one and object one. While coming to the cluster computing frameworks, Apache Spark is one of the popular in fast in-memory cluster computing. So the reason why it gained a lot of popularity is its unique data structure called resilient distributed data set, RDD. So through this, they're actually providing the fault tolerance in very effective manner when we compare with the existing cluster computing tools like MapReduce, Storm, or some other techniques. I will explain more in details now. Another thing is Spark in-memory capability. If we compare the Spark with MapReduce legacy system, Spark what it will try to do is, especially when iterative jobs, it will keep all the intermediate results in the in-memory so that it doesn't need to have the disk IOs. Usually in any computations, disk IOs are more cost effective and takes a lot of time. That might, if there are huge number of disk IOs, then that might consume a lot of time to execute that. So in order to avoid, Spark what they try to do is they try to keep all the intermediate data in memory so that further computations doesn't need to go to the IOs to access the data, and they can reutilize the same results whatever they're in the primary memory and keep proceeding the further. So that's why Spark is more popular for the iterative kind of applications and also the interactive. Another thing is Spark fault tolerance capability. Unlike if you see the traditional MapReduce framework, it used the replication to achieve the fault tolerance. In the replications, we are actually trying to replicate the data multiple times, multiple machines. So if one system fails, then the other system which has the same data try to gain that task and continue the computations. If you see the Apache Spark, if we submit any job to the Apache Spark, master node will actually draw a lineage graph. Here lineage graph is nothing but the sequence of transformations that we are actually providing in the Apache Spark. Now, that lineage graph will be distributed among all the worker nodes. If any worker node fails during the computations, the same lineage graph and the same task will be assigned to some other system. That system, instead of replicating or loading the existing data, it will try to recompute from the scratch, from where it failed. So that's the tradition. It seems to be more efficient. And other one is RDD is immutable. So we cannot change the RDD. Because of that, it gains a lot of popularity. The reason why is we are at those times while designing, they simply assume that these tools are for actually loading, doing the analytics. If we consider the huge data sets, then there will be won't be much need necessary for modifying the data. So that's why they use the RDDs as an immutable. And GraphX is actually extension of the Apache Spark, which is mainly for graph processing on a distributed environment. It providing many built-in libraries for performing the operations on the distributed graph, like finding the connected components, triangle count, and community detection, page rank. These are the few of the examples. If you see the examples shown in the slide, here it's simply taking the raw data from the Wikipedia and trying to build two different graphs, and these graphs are actually distributed among the multiple machines, then finding out the page rank and community detection, and if we join those two, we're actually getting the top 20 pages with the top 20 communities. So likewise, we can do the multiple operations with the help of graphics libraries, whatever it is provided on the distributed graphics. So we are actually motivated with these libraries provided by these graphics and Spark to implement our work. When coming to the motivations that leads to implement our thesis work, the first thing is centralized approaches. Whatever there as of now, those are not able to handle these billions of triples in an efficient manner. So we want to have a parallel query processing with the help of any traditional tools like Apache Spark or Flink. And one more thing is, my friend Hasimal has implemented the parallel RDF query processing using Apache Spark. But however, it's a basic thing and it is providing the poor performance if the queries are highly selective. Highly selectives are nothing but if any query produces very few number of results in those queries, it's actually providing very poor performance. The reason why I will explain in further slides. Mainly because of these two things, we decided to implement an advanced, sophisticated system to process the SPARQL queries. These are the key contributions in my thesis work. We proposed a Bloom filter approach to improve our previous work, parallel SPARQL query processing on Apache Spark, and also we conducted experiments on Microsoft Azure and Cloud Lab, and I measured the performance of our approach on the Microsoft Azure with 6.4 billion triples. It's around like 806 gigabytes of data. And we compared our approach with S2X and S2RDF. These are the popular techniques that are actually developed using the Apache Spark. While coming, I will also give the few of
very just quickly. So I also want to add that although Hastimal presented his thesis first, but Venu was really involved even in implementing some of the parts that Hastimal worked on, and Venu also fixed one of the problems we had in terms of how we were querying the multiple indexes, which was part of Hastimal's thesis, but there was some mistake which Venu actually corrected it and identified and corrected it. So I just want to give him that extra credit as well, although he did not list it on the contributions. Okay, yeah, go ahead.
And I would like to give the few of the existing approaches that are actually parallel query processing using Apache Spark. One thing is S2X. It stands for SPARQL on Spark with graphics. We all knew that SPARQL retrieves the data with the help of basic graph patterns in the centralized approaches. Similarly, S2X, they implemented the basic graph pattern matching algorithm using the graphics, distributed APIs. Now, what they are actually loading the RDF data, and they are processing the queries in an iterative manner. In first iteration, what they are trying to do is they are finding out the basic graph patterns for all the triple patterns independently on the distributed machines, and they want to update those results as an intermediary, and they try to keep it in primary memory and updated those results as a properties for the vertices in the existing graph. And from second iteration onwards, they keeps on validated with the adjacent neighbors till convergence is achieved. Convergence in the sense, all the vertices will have the same results. Likewise, they are doing the validations in the iterative fashion.
So you want to also say that S2X does not build any indexes.
Yes.
It loads the entire data set before processing.
Yes.
Okay?
They did not implement any kind of indexes. That is one of the drawbacks for them. And there are a couple of drawbacks that we found, and I will explain those things while explaining the performance evaluation. And another thing is S2RDF. This is the very recent paper on parallel query processing. RDF query, excuse me, RDF querying with SPARQL on Spark. They felt like data layout is the vital role for query processing, especially in the distributed environment. So they come up with a new schema for representing the original data set. The main goals to build the new schema is, one thing, they want to minimize the input data set size, and also they want to reduce the number of join operations required whenever someone posts the query on the distributed system. So another thing is they are actually using the SQL kind of interface to execute the queries. So they are compiling all the SPARQL queries into the SQL queries based on the previous data layout, and they're actually reducing based on those existing schemas, they're actually reducing the unnecessary records which are actually not needed when we post the queries.
Oh, one thing Venu, I asked you to put the right citation for that S2RDF. So just to tell the others, this is a paper published in VLDB 2016. So it's considered one of the state-of-the-art approaches that's out there for parallel RDF query processing. So Venu, make sure in your thesis report, it points to the VLDB paper and not this tech report, okay?
Sure. So I will explain our previous approach as well. This is the overview of our previous approach. They are just loading the input data and partitioning into the multiple partitions and just building the query indexes, and whenever they post the query, they are trying to execute this query on top of all the indexes in parallel. So, but here searching the indexes is more costly. So when we post the query, it's always better to reduce the number of indexes that's actually needed for a given query. So that's the one of the drawback of our previous approach. So that we improved that one in our approach. So this is the overview architecture of the previous approach. We are just taking the raw data of RDF data and converting into the property graph, and then trying to find the connected components, and then grouping those connected components, simply applying the partitions on those groups, and then storing those groups into each machine of the cluster, applying the Jena indexing using the Apache Jena, and store those indexes for the query processing. When we post the query, we are going to execute in all the indexes in parallel using the Spark APIs. That's how our previous approach works. While coming to our approach, we have, as I mentioned, searching the indexes is more costlier. So for all the queries, it doesn't need to find all the indexes, whatever created on the cluster. So we find out the possible indexes that has the query patterns, and we just queried those things. It improved a lot than the other previous approaches. So I just took the input data, and partitions into the multiple machines, and constructed the indexes and Bloom filters, which I will explain in the next slides. And whenever queries post, first it will check the Bloom filters and identify what are the possible indexes which has the possible matches for the given query. If it finds there is a possible match in the index, then only it will go to the index, load the indexes and query those indexes. So for a given query, sometimes if there are 6 indexes, there might need only 1 index to query. So we just find out that particular index and we queried only 1 out of 6.
So each index is saved in a machine, right? They are saved separately.
Yes, on the cluster. If there are 6 machines on the cluster, so we are partitioning data into these 6 machines, and we are constructing the indexes on top of those data. So here each system will have indexes only on the data it has.
So you will have index 1 through 6.
Yes.
What about your filters?
Bloom filters is also the only corresponding to the data available on that particular partition.
Are those filters also saved separately? Like,
Yes.
As you said, for example, if you have 6 machines, then each machine
has one Bloom filter only corresponding to that particular machine, only corresponding to the data that has it on that machine.
And are those filters same?
Those filters are not same with the others. other machines. Here indexes and Bloom filters are not same with the other machines. It's all Bloom filters and all indexes are unique to the particular machine. So this is the process of
so the previous slide was probably the most important part of your thesis.
Okay.
So in a few sentences, once again, just summarize how your approach is different from the previous approach,
okay.
just to make sure everybody gets the crux of it, and then we can move forward.
Okay. Suppose, yes, earlier I mentioned the highly selective queries. In highly selective queries, if there are, imagine you have the 100 machines and indexes is available on all those 100 machines. Now, if you post any query, there might be some situations where you doesn't need to query all the 100 machines. So, if here, querying in the sense we need to load that data into the in memory, and then we have to do the querying. So, this is more cost effective. So, if we find out for a given query, if we find out which indexes is having the possible matches, and if we load only those particular indexes, and if we query that, that is more efficient than the traditional. So, our
just to make sure that we don't use the word cost effective in the wrong way. So he meant more costly. Okay.
Oh, sorry. So that's why what we did in our approach is we built the Bloom filters. It's a data structure. So before directly loading the indexes and querying it, we are just to find out whether that particular index is having the possible match for a given query or not. So if it finds there is a possible match in the index, then we are loading into the memory and using the particular index for the querying. So in one of our queries, out of 6 indexes, for some queries we just need 2 indexes to get the results. So we just skipped the remaining 4 indexes and we just loaded only those 2 indexes which are necessary.
So with the old approach, without your filters,
Yeah.
When a query comes in, then you're going to load index directly
Yes.
in every computer.
Yes.
And now with your approach, before loading the index in each computer, you're going to run that filter first
Yes.
to see if the search data is in this index or not.
Yes.
If it's not, then you are not going to load the index.
Yes.
So that will improve your performance.
Yes.
Okay. And then your main contribution here is to introduce that Bloom filter within every computer,
Yes.
so that the query will be pre-processed before it gets to the index, right?
Query will not. Yes.
Okay.
So I will explain more about the Bloom filter constructions and how queries pre-processed. So this is the index construction process. As of the previous approach, we are just loading the raw RDF triples into the property graph and find the connected components in those graph, and then we are actually grouping those connected components and trying to partition the data in such a way that certain groups of connected components will become into the one particular machine, so that whenever we post any query, it is very easy to find the basic graph patterns. And then storing those groups of connected components into the machines and finding out building the indexes and then constructing the Bloom filters. Before going more into the Bloom filter construction, I will want to give an introduction about the Bloom filter and how it works. It's actually a space efficient data structure, Bloom filter. The reason why I said space efficient is it uses the bit vectors. So bit vectors in the sense it will just simply store 1 or 0s instead of storing the values. So that's why it's very space effective. So, and it is a space efficient data structure, specifies it's a probabilistic data structure specifies an element is possible in a set or not. The reason why I said possible, I will explain now. So initially the blue filter looks like this. So it all are with zeros, and below one is the indexes, and these are the bits. It will simply shows 1 or zeros. Suppose if you want to insert any string, it will do the hashing multiple times. The reason why to do the multiple hashing is, I will explain. So when I did the hashing, suppose if I want to insert the string umkc, it did 2 times hashing and it get the index. So the corresponding index position will make it 1. So if you want to retrieve and if you want to check whether a string exists in the Bloom filter or not, what it will do, it will follow this, it will do the same hashing, and it will find the corresponding index position and check that index position in the Bloom filter, it is 1 or 0. If it is 1, means that particular element is there in the Bloom filter. If it is 0, it will say that particular Bloom filter is, that particular element is not there in the Bloom filter. Now, suppose there is a scenario, if I want to insert some other string, like my name, if I do the same hashing, it may provide the index position 7. So even though that particular string is not inserted in the Bloom filter, but that corresponding index position is 1. So that means even though that particular string is not available in the Bloom filter, it gives the false result. That we call as a false positive. So that's why I mentioned that it's a probabilistic data structure. It says whether an element exists or not. So sometimes it may give the false positive. So we need to tune the Bloom filters while constructing based on the number of elements. So we can also reduce these false positives by doing the multiple hashes, multiple hash functions. There are multiple algorithms available to find out the number of hash functions and finding out the false positive rate for a given Bloom filter based on the number of elements. I've used one of the popular approach to find in my implementation, to find the number of hashes and number of hash functions and the false positive rate. And I forgot to mention, Spark 2.0 recent version is providing an algorithm to find out the number of hash functions for a given Bloom filter and also the false positive rate for a given Bloom filter based on the number of elements.
So your filter is basically just a hash table, right?
It's not a hash table.
Based on what you said here, like whenever you have a data saved, for example, in the index, then you will set the corresponding bit to 1, meaning that that data is in the index.
Yes.
And as you said, chance exists that you may have non-existing data that corresponds to the same hash key,
Yeah.
right? That is what you call a false positive. So basically, you introduce this hash table here. Before you search index, you search this hash table first.
Yes. There are, I constructed 6 Bloom filters on top of each indexes. I will tell you in next slides. So Bloom filter construction or implementation in my approach. So suppose if this is a string, subject, predicate, object, I mentioned there are 6 canonical forms or 6 possible triple patterns. Triple patterns are nothing but the triples that are there in the SPARQL query, which we need to find out certain variables. So if we take any of these triple, there are 6 possible canonical forms that particular thing. So one of these particular 6 canonical forms should be there in the triple pattern of the SPARQL query. So what we did is, on each index, on each machine, we constructed 6 Bloom filters. Each Bloom filter will store only one kind of canonical form. So if you see here, this is for triple pattern of, we need to find out the subject and predicate and object. this is for one kind of canonical form, this is for another kind of canonical form, this is for another kind of canonical form. So for each triple in that particular index, we find the canonical forms, 6 different canonical forms, or 6 different possible ways that it can query it. And we inserted that particular canonical form into the appropriate Bloom filters. Clear? I will explain again. So we do have Bloom filters implemented separately on each and every indexes on each and every machines. If we consider one particular machine, it has 6 different Bloom filters again on each index. So what it will do is it will pass the every RDF triple in the data, whatever data it has on that particular partition, find all 6 possible canonical forms for that particular single triple. Either sometime all the triple, I will write here.
Does that mean you have 6 hash tables?
Yes.
And then for every triple,
Yes.
you get different hash values
Yes.
for each table.
So suppose for this triple, sometimes subject might be missing in the SPARQL query. So we have just predicate and object. So this is one canonical form, and subject is there. We might need to find out the predicate. Object will be there. So this is one kind of canonical forms. So for a single triple, there are 6 different canonical forms will be there. So for each and every triple in that particular partition, we find out all the canonical forms for all the triples, and we inserted those canonical forms into the Bloom filters. So one Bloom filter will hold only one kind of canonical forms. So we assign the IDs to each and every Bloom filter, means here to each and every pattern, mean to say. So these IDs will be helpful in loading the Bloom filters into the memory. If you are very clear, then I will move to the further step.
Okay, Venu, you may want to explain how this work was inspired by one of our previous publication and how it is different. That's important.
The motivation to implement the Bloom filter is one of the RDF query processing that is for quadruples. In that particular, but it doesn't has for the triple format. So we motivated with that particular research, and we implemented the Bloom filter approach over here. So there, it's actually find quadruples. So along with the subject, predicate, and object, there will be a context. That context specify which particular graph or which particular RDF database, which particular knowledge base that particular triple belongs to. That's specified by the context. So that is for altogether different approach. So there they are using 7 different Bloom filters. Here we just use 6 different Bloom filters, but in that particular approach, they are using 7 different Bloom filters. Each Bloom filter will hold for one canonical form, same as here, but the another one is for, if you see the quadruples, there are 4 strings will be there, like subject, predicate, and object, there will be one more string. So here, sometimes the missing value might be the context as well. So we may need to have the Bloom filter for one more canonical form for subject, predicate, and object. So there they are using these Bloom filters for, instead of directly going to the indexing, they are using this Bloom filter to check, and they are doing the further processing. So mainly motivated because of that particular approach. This is actually published by Dr. Vasil and Anas.
So just to tell, you mentioned that all 7 filters in that approach are Bloom filters. Just to correct, the filter for canonical form SPO is a Bloom filter in that approach. All the others are counting Bloom filters because of the nature we decided to index the graphs. Okay? So in this approach, you are using Bloom filters for all the 6 canonical forms, just for simplification reasons. But you can very well use counting Bloom filters, and that should be okay as well.
Okay.
So good. So good explanation. So keep going.
Is this how you reduce that false positive you mentioned?
False positive rate, no. False positive rate, I have, there is a formula. If you provide the number of elements, then it will give the false positive rate that we can utilize. I mean, these parameters are required while creating the Bloom filters.
So it's not addressed by this one, right?
No.
Okay.
I think Dr. Zhang's question is very interesting. Like, in a way, this architecture reduces false positives because we are having 6 different checks that we will do before we decide whether to load an index or not.
Right, that's
If
what
we
I
could have
thought.
kept one single Bloom filter, but then we would have increased the chances of false positives. So it's actually very relevant to what he asked. Okay, so does that make sense? You may want to repeat, kind of discuss this aspect. If you have one single Bloom filter, then you're more likely to have more false positives. But when you partition it and store items separately, and you're going to check each of them, the chances of having false positives will be lower using smaller Bloom filters. So, okay, the collision rate will be lower. Okay, so that's important. So good question, Jayamji.
Now the interesting thing is how query is processed. So once user executes any query, the first thing is it will parse the triple patterns in that particular query and find out which pattern it is. And as I mentioned earlier, if you see on Bloom filters, we provided an index that we called as an ID for that particular pattern. So we find out the pattern and the corresponding ID. In these patterns, list of patterns, we find out which particular Bloom filters are needed. So we constructed 6 Bloom filters. So even in those 6 Bloom filters, we doesn't need all the Bloom filters to be loaded. So we find out which particular Bloom filters are required based on these pattern IDs. So we've only loaded that particular Bloom filters into the memory. And then we find out for each triple pattern, we checked in that particular Bloom filters if there is any matches in that Bloom filter exists or not. If there are no matches, then don't load this path. Don't load this path indexes into the memory. If there is a match, here match in the sense all the triple patterns in the query should be there in the should be there in the Bloom filters. If all the triple patterns are there in the Bloom filter, then only it will load the index. If it finds one single pattern or 2 triple patterns did not find in the Bloom filters, then it won't load that. And similar process will be carried out in all the machines in parallel and aggregates those results using the SPARQL APIs and produce the final output. This is how the query is processed. Any questions in this? Now, while going to the performance evaluation.
Before you go further, so I think you mentioned you are going to load the index into memory, but essentially the index is disk space. So what you must say is you're going to query the index, okay? So because that index is actually disk based and not main memory based because you're using TDB, right?
Yeah.
TDB. So only when the Bloom filters tell you that yes, there is a chance that you may find results by searching the index, you proceed to query that index. And if the Bloom filter test fails, you ignore that index and don't even touch it.
Yeah.
Okay. So that's the key idea.
So that's how we actually eliminated to query the unnecessary indexes, because here searching these indexes is very, very costly, take lot of time. So we try to reduce those searches in searching the unnecessary indexes. So while coming to the performance evaluation, I use the real dataset from the data gov. It's having almost 6.4 billions of triples from multiple sources of around like 4,000 different files. We combine it into a single file, and we use that particular one to conduct the experiments. So here we consider one primary assumption that given RDF data set has the multiple connected components. Okay. There are some existing approaches that actually partitions the graph into the small size RDF triples, but here to provide the more number of connected components in the given data set, we remove certain triples which has the predicate type. Those are actually general types of predicates. If we remove those, then we can get the multiple connected components in the given data set. So I removed those predicates, then we got the number of triples of 6.4 billions approximately, and from those we got unique subjects of 0.5 million, and predicates is 3,514, and objects, and these are the number of connected components in the given data set. So I also did connected the experiments on another data set. It's a simple 14.5 gigabytes of file size, and the number of predicates is 99 million, and the number of unique subjects, predicates, and the number of connected components is 2192. This is a DataGov dataset. It's actually open source dataset. So I have used five different query patterns, 5 different queries. Each query is having the operators join, union operator. One query is having join and optional multiple operators, and multi-level join, and join and filter. And this query produces the results of 4,382 records, and this one is producing 36. This is very highly selective. That's what we can say that. And query 3 is 85,189 records. And if you see, these are the number of triple patterns in that query. Query 1 has just 2 triple patterns, query 3 has 5, query 4 has 6 triple patterns, and query 5 is having 2 triple patterns. So I have conducted the experiments on 2 different cluster platforms. One is Microsoft Azure. Microsoft Azure is not an open source, it's a paid version. I need to thank Dr. Rao for providing the sponsorship to conduct the experiments. Microsoft Azure, I just used cluster for our subscription. It restricted to use only the 6 nodes. So we just used 6 worker nodes and 1 master node. And I have also conducted the experiments on open source cloud platform called Cloud Lab. In this, we used 16 machines, 1 master node and 6 worker nodes. And the resources on these 2 cloud platforms are shown here. If we see the first Microsoft Azure, the number of master node is 1, and also on the Cloud Lab 1, and number of worker nodes. Number of worker nodes we can also call as a executor nodes. So here in the Microsoft Azure, I just use 6, and on Cloud Lab 16, and RAM size, Microsoft Azure is providing 32 gigabytes, and Cloud Lab is providing 64 gigabytes. And number of cores in each machine on Microsoft Azure, it is providing 8 cores. Altogether, for the overall cluster, 56 cores are there for all the machines. On the Cloud Lab, we got 136 cores, but Cloud Lab is restricting in storage. So it's simply providing 128 gigabytes of storage. So that is not enough to conduct the experiment for dataset 1. So that's the reason why we also choose the Microsoft Azure to conduct the experiments. But Microsoft Azure is providing 1 terabyte of storage. So the operating system, we are using Ubuntu on both the cloud platforms. So these are the software configuration that we use: JDK 1.8, Scala 2.7.7, and Spark 2.0.0. The reason why we use the Spark recent version is it's providing APIs for Bloom filters. So this is also providing the algorithm to find out the false positive rate defaultly based on the number of elements we provided, and also the false positive rate for a given number of elements. And Hadoop 2.7 and Xena 3.0.1. And these are the basic software, Spark configurations that I modified based on the clusters. While coming to the, this is the master node and number of executors. Here, the executors are nothing but the worker nodes. Number of worker nodes are 6 in the Azure and 16 in the Cloud Lab. And executor memory is the amount of memory required for certain transformations in the Spark to save into the RD, to serialize and deserialize the data. So the maximum limit is 28 gigabytes. Number of executor cores means the number of cores to be participated in any computation on worker node, on each worker node, 8 cores. And this is the driver memory, means on each worker node, the maximum amount of RAM memory that it can utilize to computations, 28 gigabytes. And the number of cores on master node, this is for, and default parallelism. This particular parameter will specify number of different kinds of tasks that it can do without interfering with other cores. So this particular parameter can be calculated based on the number of executor nodes and the number of cores on each executor. So based on, if we multiply both, that many parallel tasks that we can, maximum number of parallel tasks that we can perform on Spark cluster. And driver.max result size. This particular parameter is for, suppose if you want to serialize the data, as Spark loads the data into the distributed environment, it will serialize or deserialize into the blocks manner. So the maximum block manner, the maximum block size that it can, maximum block size is the 4 gigabytes. So if there is any block, these blocks will be divided based on the input data set. So if we provide more data set and less number of worker nodes, the block size might increase, and those times it might throw the errors. And the Spark network timeout. In the process of computations, worker nodes are Spark and master node might need to communicate with each other. So if it could not able to communicate within the 300 seconds, then it will fail. So these are the configurations that we modify for performance tuning. Especially all these parameters are used for shuffling. In the process of computations, there are some transformations they might need to shuffle the data between the multiple worker nodes. So in that process, instead of directly sending the data, we are using the compressions, and the corresponding compression technology is LZ4. By default, it is providing the Snappy. LZ4 is the most efficient one, this is one of the Java APIs. So we use this particular compression technology to compress the data before sending between the multiple worker nodes. And this is the way to run our program. We mainly divided our program into the 4 different modules. First module is to group the connected components from the raw data set, and then we perform the indexing. The reason why to modularize is we can, at any point of time, we can run only that particular module instead of running everything from the scratch and in a single program. And the Bloom filters, we can construct separately, and the query processing. So all these 3 tasks are one-time execution, and this one we can run any number of times. And this is the execution time for the index construction. This is the amount of time taken in seconds for finding the connected components on dataset 1, and this is for dataset 2. This is for grouping of connected components, and this is for indexing, and for the Bloom filter construction. We doesn't really worried about these particular times because all these execution times are for one-time execution. We doesn't need to, these are not really consider for the performing the in the evolution of our performance?
No, maybe you should say it better by saying indexing is a one-time cost, whereas query processing, happens periodically. Okay, so you index the data once and then you execute many queries. So even if we are slow in indexing, it is still okay because our priority is to get maximum out of query processing or to get the best performance during query processing.
Okay.
Okay.
Yeah. These are the intermediate statistics we collected on each and every machine. As I mentioned, here in these statistics are for dataset 1 that we collected on Microsoft Azure. So this is for 806 gigabytes. So we partitioned into 6 different worker nodes or master nodes, and these are the index sizes on each and every machine. This is partition 1 and machine 1, 114.1 gigabytes of index file size, and 7.41 is the Bloom filter size. We serialize those Bloom filters and indexes onto each and every machine, and we find out those sizes. So some Bloom filter size is 7.41 gigabytes, and if we consider the number of records, number of elements in that particular Bloom filter, this is the 0.8 billions in single Bloom filter. We have 6 different Bloom filters on each index, so this is for one index. So this is for one particular Bloom filter in one index, in machine 1. This is for, and the number of elements on machine 2, this is around 1 billion, and similarly for 3, 4, 5, 6, those are the index sizes, Bloom filter sizes, and the capacity for Bloom filter.
So for Bloom filter size, that's 6 filters combined, right?
This is for single Bloom filter. And on the remaining Bloom filters, the number of elements will be the same.
No, I'm talking about the column in the middle.
Yeah, this is the combined one.
Like 6 filters combined, you have, for example, for the first one you have 7.41.
Yes, this is for all 6, combined for all the 6.
Okay. For these filters, are they constructed at the same time with the index?
Yes, same time during the index processing.
Okay, so do you have to update them? Like, for example, when new data comes in or when existing data is removed, do you have to maintain those filters?
Yeah, it's better to rerun the index processing if we update the data sets.
So it will be constructed, updated at the same time as indexes?
Yes.
Have you thought about?
So in this work, so Dr. Zhang, yes, a good question about the update. In this work, of course, we did not consider updating the index in real time. We assumed it's more like a data analytics workload. But yes, if we add a new triple, then we have to insert that triple into the index and update the Bloom filter to make sure the data in the index and the content in the Bloom filter are consistent. And just to add one more point, the number that you see, Bloom filter capacity, that essentially tells you how many triples are stored in each partition. So if you add it all up, it should come close to 6.4 billion triples. So in a way, our partitioning strategy, which is quite simple, where we actually removed certain triples to make the graph, one big graph, disconnected, actually worked pretty well, So you can see kind of almost evenly divided the triples across the, the 6 nodes that were there, the cluster. Usually it's very difficult to achieve this because if the data set is highly skewed, and when you do data partitioning, you may have certain nodes that get too many triples and some get very few triples. And interestingly, for this data set, we didn't have that issue, but I'm sure, this cannot be overlooked for other data sets. So, but that's what the number means, the one in the last.
So this is the important and crucial task in my thesis for the execution times. So as I mentioned, we compared our approach with our previous approach and also the S2X. We could not able to compare our approach with the S2RDF. The reason why is it is storing, it is generating a lot of intermediate data. So if we take the input data set size of 1 terabyte, it's generating almost like 11x times 11 terabytes of data. We did not, we ran that S2RDF, but it ran for 10 days and still it's not showing any progress, so we simply kill the job. And also storage is one of the limitation for that. So we just compared our approach with the Bloom filter, with our previous and S2X, and these are the results for the S2X, and this is for our previous approach, and the green ones are for our approach, Bloom filter approach. So these are the execution times which are highlighted. If you see, our approach is showing better performance when we compare with any other things. And these are the possible, in brackets, we highlighted the number of matches. Number of matches for that, these are actually, for query 1, out of 6 indexes, only 2 indexes is having the possible matches. And for query 2, out of 6, only 2 has the possible matches. And query 4, out of 6, only 3 has the possible matches. So this is the number of matches and this is the amount of time taken. And this particular one is for cold caching. There are 2 different scenarios we took the execution times. One is the cold caching. Cold caching is nothing but initially nothing will be there in memory. So we have to everything the data loaded into the in memory and then do the evaluation. When we ran multiple times, the previous Spark can able to store the intermediate results in memory. So it doesn't need to have the additional time to read the data from the disks. So it is much faster for the executions. So we also took the execution times on the warm caching, which means the certain data is already there in the in-memory, so we evaluated. In those cases, our approach is much better and it is showing the reduction of performance almost like 50% when we compare with our previous. The reason why is here, we don't even need to reload the Bloom filters also. Bloom filters and everything will be there in the in-memory, so it can be directly do the finding out the possible matches. Here green ones, as I mentioned earlier slide, green ones are our approach and black ones is our previous approach and red ones are for S2X. Our approach is almost like nearly 45% of our previous approach.
So basically, the addition of Bloom filters, which Venu did, helped us improve our previous performance result by almost 100%. Okay, so that's the kind of conclusion.
These are the query execution times on data set 2. Here on the data set 2, we could able to perform and we could able to compare with S2RDF as well. Since it's a small data set, it's a 14.5 gigabytes of data. If we see the green ones are our approach and black ones are our previous approach, and the blue ones are the S2RDF and red ones are the S2X. In few cases, the S2RDF dominates our previous approach. But if we compare with our recent approach, this one it is more efficient. It's taking very less time when we compare with in all the cases with all the approaches. And for this particular one, we have the 16 indexes, and out of 16, query 1 has just 4 indexes is possible matches, and query 2 is having only 3. Query 3 is having 4. And query 4 is having the 6 possible matches, and query 5 is having just 5. So even in this case, our Bloomfield, this is for cold caching on data set 2 in comparison with S2X, S2RDF and our previous approach. And these are for the warm caching. Here, as I mentioned earlier, warm caching is providing more better results than cold caching. Even our approach is more better efficient than the cold caching. So here it is again almost like our approach is far better than any of the existing approaches, and the query execution time is almost like 30% of our previous approaches.
And one thing to you may want to comment is S2RDF is still considered the best out there. and was published in a leading journal. So, while these results look very promising, but in fact we wish we could have tested S2RDF on 6.4 billion and said that we are actually better on very large data sets. But unfortunately, as Venu mentioned, we could not run S2RDF on Azure because as he said, it ran for 11 days, just wasted money and did not yield any results. But we hope we can at some point be able to run S2RDF on a much larger data set. So Venu kind of summarize the results, like summarize in a few words what these results mean to us.
So if you compare in overall, both all the approaches, if you consider the pre-processing times, even if you compare the pre-processing times with S2RDF, our approach is comparatively very less in doing that. And also if you see the query execution times, if we our approach is almost like more than 100 and almost 6 times lesser than the S2X, and also the 35 to 40% lesser than the S2RDF, which is one of popular leading parallel processing using Apache Spark, and 30 to 40% lesser than our previous approaches in all the cases, cold caching and warm caching in both the datasets, dataset 1 and dataset 2. So based on this, we can clearly claim that our approach is more efficient than any of the existing approaches that are actually developed using Apache Spark. And when coming to the conclusion, our approach is simply finds the connected components from the given loaded property graph and finds the connected components, perform partitions on the group data, build the indexes. And we use the Bloom filters on top of the indexes, which will find the possible matches and executes whenever we pose the query, it executes only on the possible indexes having the possible matches, and skip the executions on skip the searching the remaining indexes, which improve the performance far better than the previous approaches and the existing approaches. I would like to thank NSF for providing the funding for one of the semester, and I would like to thank Microsoft Azure for providing me to conduct the experiments. If there are any queries.
So let's first thank Venu for an awesome presentation. So let's give him a big round of applause. So now it's time for Q&A. So anybody in the audience, if you like to ask any questions, please do. Then after that, only the committee members will discuss in the room, and everybody else has to leave. And then we will discuss and then call Venu back to the room to give our final verdict. So any questions from the audience?
What were the hardest things you had to deal with when constructing all this?
The hardest time is to fix the previous error. Issue, there was one error issue. That one is like our previous approach used the Hadoop. Hadoop, they are using Yarn as a resource managers. So if we if we use 16 worker machines for one computations, let's see, let's think just 8 machines involved in the computations out of 16. If we construct the indexes, if we run the indexing construction program, out of 16, only 8 machines is having the indexes. And if you run the query processing, there are some situations, out of 8, only 4 are involved in the computation of query processing. Even though here we are assuming that all the 16 have that, but only 4, all the systems are not involved in the computation, since we are depending upon the third-party resource manager. Yeah, here Spark doesn't have any control over taking the number of executors. So in those cases, the executors which are actually part of index construction, those are not involved in the query processing. So we did not get the full results at one shot. So they have to run multiple times based to get the final results and aggregation, to do the aggregation. Any other question?
No more questions here.
Thank you. Thank you, Doctor.